And we're live. Yes. Should be live. Oh, we've got a great stream prepped for you guys today. It's a round 2. Some of you might remember the last time we had this little board in the shop. This is a little buck converter module that we made as a prototype after we realized that our old design wasn't going to work very well. And what we've done is, well, we've made it a little better. So we changed the hole spacing. We're now using a standard hole spacing, so voltage in, voltage out, ground on the bottom. And sure, we had to twist some of the tracers around a little bit, but I think overall that is a huge step in the right direction. Sorry about that. There we go. Got her focused. So same general concept, same module, same design. A little more input capacitance, a little more output capacitance. It's pretty sweet. Apologies about the voice. A little under the weather. Hopefully it comes across just fine. If I'm clearing my throat a little bit, that is why. So yeah, basically the reason why we need to revisit this is because after we finished our last video on this module, we realized it didn't work too well. We didn't have enough output capacitance. And there were only, I think, like 2 pads. Yeah, there's only 2 pads for output capacitors. So here we've got some sweet pads. We've got some pads for aluminum polymer caps, some electrolytics, and then plenty of MLCCs. So we should be able to get this thing going. Oh, and it's adjustable output now. So you'll notice I put some comments on the bottom. This is meant to be more of like a, an off-the-shelf sort of thing, where you could grab this module and use it for more than just one thing. So basically you can go up to 4.5 amps out, 0.8 volts up to your input voltage because it's a buck module, and then up to 40 volts on the input. So yeah, general purpose DCDC module. It's gonna be sweet. Alright, I'm getting a message here. Bear with me a moment. I'm going to try to use the new control room. But the new control room doesn't let me see the stream. That's not great. Anyways, welcome. Looks like we got a couple people dropping in. Glad to have you. Oh, and there's one more awesome thing. We added new camera angle. You guys were asking for this. So we've got a top-down sort of view that should work a treat. Looks like we're getting a little bit of glare. That's alright. I'll be mindful of that. So when we're doing some soldering and the top-down view makes sense, we can use it. I'm pumped. I hope you're excited too. Okay, I guess that leads pretty well into where we're headed. So what we've got going on here is we've got our capacitors, inductors, all that fun stuff. We've got some of those components laid out here. I think we'll start with those. I think we'll start by putting a couple controllers down with a couple inductors. Excellent. We're going to get some soldering done. It's going to be a very fun time. Yes. So, if you had any questions about how to solder, all that nonsense, just throw it in the comments. We're watching that, so I'll try to answer them as we go. Cool. Got 2 controllers from our last batch. Let's see what we got for LEDs. Got a couple of those. Sweet. Mm-hmm. Okay. Yeah, I feel like I tried to tell you all what we were going to do today on the stream, and I just got excited and distracted. That never happens. But yeah, it's basically just testing the new buck design. Testing the new buck design. Yep, I've got a feeling this is going to go much better. Or at least, it better, because this is the buck converter design that we're using on the UPS project. The last version of the UPS project, I've got the mainboard schematic ready to rock and roll, working on the layout. So it's getting close. It's getting very exciting. Welcome, guys. Welcome to the stream. Yeah. This is an old soldering jig we made a while back. Some of you that have been around a while probably recognize it. It's basically just a big aluminum angle and a couple big magnets on an old computer side panel. That way we can slot a couple boards in here, no problem. And it holds them nice and securely so we can get our work done. It's pretty great. This is one of those little things that we did a while back that is just so useful, because I've got, you know, one of those cheap Chinese board holders that spin. Oh, they're just not great. I'm getting a little bit of glare. I'll try switching back to the main camera. We'll go back and forth. Just let me know. But oh my, I think it's just time to get going. I guess we're building 3 of these because I don't know. 3 boards looks like the right amount to me. 3 of these looks like the right amount. Okay. Getting the iron heated up. There's nothing like the sound of a soldering iron hitting the sponge for the first time. There's no better way to start the day. That's awesome. What I'm doing is there's a thermal pad underneath these controllers and on these diodes, and we're just adding a bit of solder here. Now, if we were making these as a production board, what you would see is the use of solder paste. Since we're doing this by hand, you don't have a solder stencil. This is basically just doing the best you can with what you got. Rather than using a paste, which is like some solder that's mixed up very well with a little bit of flux, we've got our separate flux, we've got our separate paste. Our paste is basically, you know, the actual solder itself. So we've got the solder, we've got the flux, and it'll get on there just fine. Getting the controllers out. I'm gonna need 3 of these. Hello, the Arduino guy. How's it going? It's been a while since I've heard from you. Hope life's going well. Holidays are treating you kindly. What in the world? Where's our ICs? There. Yeah. Hope you like what we got going on today. I'm pretty excited. Like with where our UPS project is, this is one of those. I just want to make sure. Everything's okay. I want to make sure everything's ready to go. Because if we get down the end of this road, if we build our main board and like the buck modules are the problem, I'm gonna be so furious because we're gonna have these giant power converters that are moving thousands of watts, high voltage, isolation, all that nonsense. And if you get down to the end of that road and your DC to DC converter, your little, basically off the shelf, nearly no analysis, well, relatively small amount of analysis required, and that's what's giving you grief, whew, that's not where you want to be. So that's why I made this little dev kit. Yeah, oh, by the way, schematics linked in the description. If you want to take a look at what we're building, I should be able to find this. That's available for everyone. Full design files are available on our Patreon. Oh, yeah, that's one of the things I wanted to talk about with you guys, actually. I wanted to talk with you guys about that. So, if you've been around the channel a while, you'll already know this, so sorry if this is old news for you, but one of the main things that gets me excited in our projects is the opportunity to teach and share knowledge. That gets me very, very excited. That's a part of the channel that I hold pretty near to my heart. And it's like, we're doing fine. We're gonna keep doing our projects no matter what. But everything costs money, and if some of the folks in the community, really like what we're doing and they want to help us out, I want to make sure that there's a mechanism for you to do that. Because, obviously I feel pretty strongly about the mission, and it's like, yeah, if you feel strongly too, I want you to be able to help out. And for a while, we were kind of managing that through Amazon affiliate program. But they decided that they didn't need us, and quite frankly they don't. They're gigantic. But just that the community was a little too small for what they were looking for, so they shut us down, so to speak. So I was like, alright, not Amazon affiliate, gotta find something else. And so that's why we're giving Patreon a shot. So yeah, just want to make sure that opportunity stays open. Speaking of opportunity, soldering this module down. So we're doing a reflow process right now, and basically all that means is there was solder on there. It was once molten. We are making it molten again. We are flowing the solder again. Reflow. It's critically important, especially for this regulator, because there's a big heat slug on the bottom of this part. And that heat slug is basically how the controller stays cool. It's got an integrated MOSFET right inside of the package. Does some peak current limiting. It's a pretty sweet part. But in order for it to really work, we gotta keep it cool. So there's some vias right underneath that pad that take that heat, sink it straight to the ground plane. Oh, we're almost there. We're almost there. I can feel the solder kinda. Almost. And this thing's gonna be smoking hot. So we basically have to heat up the whole ground plane for this thing to let us solder it down. Oh, wow. Oh, you know what? We were messing the hot air gun set to the wrong temperature. That's what's going on. It's like, man, this is taking a long time. We were doing our testing of the temperature monitor project. My iron was set to 200°C. Yeah, that'll do it. Alright, 350. We're back up to normal. Sorry about that, guys. Sorry about that. Alright. This time for sure. Yes, that feels a little warmer. That feels like I remember. There we go. There we go. Controller's down. Let's get our rectifier diode. Good shape. There it is. There, that takes much less time. So basically we just preheated the board. Huh? Yes, yes. Yeah, I always like getting in the shop. Okay. PCB the second. Bet this will take a little bit less time, huh? Yeah, one thing to think about, I'll just keep rambling while you guys are watching, but one thing to think about when you're making a footprint for a component like this with the thermal pads is solder likes to wick. So if your holes are too big in your pad, it can basically steal all the solder meant to be on that joint, meant to give you that thermal junction, that thermal interface. Come on now. Ugh. There you go. And it can just suck all that right down through your thermal pad and leave you in pretty sorry shape. Where there's a lot of voiding and it doesn't have good thermal contact, things can start to break down pretty quickly. So it's very important that you keep those holes small. General rule of thumb that I've used in the past is 0.2 millimeters or 10 mils. That's generally what I've seen is the accepted threshold wear. You will not have any major issues. Alright, moving on up. These are really the only tricky parts to get on the board. Once these are on, we are pretty much home free. Just a couple simple passives. Oh yeah, and once we get these assembled, we're going to be doing line regulation, load regulation, all kinds of testing. So it'll be great. The main thing that we're looking for is to make sure that we're not triggering the like the overcurrent hiccup mode. Because basically what we were doing is there was too much output voltage ripple. I think there's too much output voltage ripple, and that was triggering one of the many protection modes built into this IC. There you go. Yes, yes. Switch mode power supplies. Oof. Can't beat them. Oof. Oh boy, sorry about that glare. I suppose that's what happens when you put a camera directly underneath a light. Sometimes light reflects. Well, maybe this is like a pros cons moment. Good news, bad news moment. The good news is that my table's level. Alright, so that doesn't look like it wet terribly well. Maybe a little more flux on there. I can see that it didn't really wet up the pad. Actually, let's break out the microscope. I want to highlight this. Where is it? Light. Microscope. Sweet. So basically, here's what I saw when I finished that solder joint. Oh, one moment. Oh boy. Oh, now I've done it. There it is. Alright. Focus. There it is. That's what I saw. It's just kind of hanging out. It's not really wetting to the part. It's just kind of there. So added a little bit of flux, reheated it. Let's see that over here. Let's see that on another component. Okay, see that? See how it's not really wetted on that pad on the left? Added a little bit of flux. We're going to heat that up again. And hopefully we'll see that wick right around. Oh, that one might have not had enough. Alright, we can get a little more on there. Yeah, much better. Much better. Excellent. Okay. Controllers are down. What does that mean? Well, I think that means it's time to solder some of the leads of this controller. So you will notice, there we go, got the exposure set. You'll notice all we did was the thermal pad. We didn't actually solder the proper terminals. This is basically a dip. I think it's got 2.54 millimeter spacing, so it's not that big of a deal. We can get that soldered, no problem. Right in a hurry. Shouldn't have many problems with bridging. All we gotta do is touch off on each of these pads. Get just the tiniest little bit of solder on there. There we go. Coming around the other side. Basically, more of the same. There we go. Rinse and repeat. So we're just going to make our way around the rest of these controllers. Shouldn't take too long. Shouldn't take too long at all. Yes. I don't know. I hope you guys are getting excited about the upcoming EPS videos, because if you like what we're doing today, if you like getting in the shop, it's gonna be a fun couple weeks when we have those prototypes to dive into. I've been starting to think about that, right? Making sure we have test points where we need them. Making sure that we're kind of ready for those next steps. And yeah, basically I think what we're going to do is we're going to reconstruct the old UPS with new hardware. Because, I mean, right now our plan... Oh, if you follow us on Twitter, look back a week, 2 weeks. Oh boy, it all blurs together. I don't even know, but look back a little while. You'll see one of our latest tweets is an image of our layout tool in KiCad, so we're in PCB new. And I just loaded in all the footprints, right? We're not really doing proper layout yet. Well, we're just getting started, but not on that module. That one, just the schematic is done. And basically, I pulled in all the footprints, and I pulled in the board outline, and they were just these massive transformers, like boom, 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 boom. And I was like, there's not even enough XY space. Like, there's not even enough horizontal and vertical space to fit just the transformers on this board. So we had like 4 or 5 massive transformers and inductors. It was absolutely incredible. You know what? Let me know if the stream sounds good. I'm gonna hop into our stream for just a moment. Let me know if the stream sounds good. Yup, there it is. Sounds great. Hey JD, welcome, welcome. Glad you made it, even if you never get notified. We're doing round 2 of the buck converters. I don't know if you scrubbed through already, but ho ho ho. Sorry, I just saw that. I thought you said hi. No, ho ho ho. Hi. Happy holidays, JD. Happy to have you in the shop. Yeah. So we had this old module that we basically slapped together. Didn't work too great. And I've got a new dev kit that has 0.1 inch spacing, so you could like drop it on a breadboard if you needed to, that kind of stuff. We've got some options to get some aluminum polymer caps on, some electrolytics, and more output capacitance. Because why we only put 2 pads on there last time? No idea. Nobody knows. Plus adjustable output. And some pretty silk screen. We just got the controllers on. A little bit more to do, but not too bad. We'll be off and running in just a moment. Oh, and also this. Also that. I'm pretty pumped. Should be an awesome stream today. Speaking of awesome, we got some variable resistors here. Got some trim pots. So this is actually made so that it can be adjustable output. So when we're doing our testing, we can tweak a potentiometer to change the set output voltage. That's kind of stuff that gets me excited, so we can test them all without, so we've got a 3, a 5, a 12, a 15. This will let us kind of check the efficiency, 2 different configurations, see how we're doing. Okay, so we're gonna need a little bit of solder. Oh, these are kind of tricky to reflow. We used some of these on, which project was it? I think we used them on the old UPS, because the way that our analog amplifier was set up, you had to like calibrate it after the fact. It was not the best, but you had to like calibrate it to set the gain the same for the line and neutral, because for some reason that's the way that I constructed the voltage amplifier. Yeah, I don't know. Maybe I was having an off day or something. But anyways, basically what we did is we had to tweak these potentiometers, and I noticed that if you heat them up a little too much, they tend to just self-destruct. And you can't really spin them anymore. It gets kind of nasty. So we're going to try to avoid that today. We're going to try to avoid that. Oh, sorry, I'm just a touch out of frame. on, pretty easy. The focus is real. We can see how he did in just a moment. Yeah, I probably want to check this one out. I think I want to check those, because I was trying to keep a pretty light touch. And yeah, I'd hate to have one of those be not soldered down and peg our output voltage to something ridiculous. So we'll just ohm these out real quick. They're all set at 50%, so we'd expect them to all read about 100K. Oh my goodness, that glare is punishing. Punishing, I say. Okay. You can see that. Got it in ohm mode. We're just gonna check over to our feedback. V out. 200K? What? Oh, look at that. Yeah, this should be 250, just like I said. Yeah. Cool. Seems like we're all good. Yeah, nice. You got the trimmers on. Okay. And I think we'll circle back, do all the little components. Alright, so we're into the proper meat of this bill of materials. We've got, what do we have? We have the diode installed. We've got, alright, I'll just check these off. We've got the diode installed. We do not have the ferrite bead installed. We do not have the inductor. We have the controllers. And we've got the variable resistor. Okay. There are just a couple resistors on here, so let's do those next. We need a 2.15 K ohm resistor. We're in the 1K decade. 2.15. Grab the tweezers. We're going to need 3 of these, populated as R6. Looks like these are keeping our LEDs in check. What else? Anything else in this decade? Yes, we've got a 7.5K, and that is populated as R5. Oh, by the way, JD, we got schematic linked in the description if you want to follow along there. No worries, should be set to public and all that. If not, let me know. I can try to fix that live. Okay, so we got the 7.15, we've got the 2.15. What else? Do we have anything else in this decade? Nope, that's all I'm seeing. Alright, we'll get those soldered down. Yes, yes. We'll see how I did. I remember last time we made this board, I had some issues soldering the ends of these components that are tied to the planes. I had some issues getting those soldered down. And if I'm remembering correctly, it was because our thermal reliefs were just a little too thick. So I tweaked it. Oh no. I lost one of our 7.15K resistors. And those are going as, what is it? R5? Yeah, those are R5. Part of our feedback. Dope. My goodness, I'm dropping those like crazy. Butterfingers this morning. That's okay. It's okay. They make them in factories every day. Grabbing a couple more. Yeah. Oh my. Oh man, these tweezers. I've got a magnetizer demagnetizer on my Christmas list. Let me just say that. These things all over the place. I don't know how it happens to tweezers, but it's like use them in the shop enough and they just get energized eventually, or magnetized eventually. I'm just thankful the tips are still pretty sharp. Okay, circling back around. Alright, they spliced my solder. There's like this weird double thick spot. Oh, looks like we're still having a bit of trouble with the planes. That's alright. We can get iron directly on that pad, and that helps a lot. There it is. Nailed it. Thanks. I'm glad you like the top down. Glad you like the top down. The glare's driving me nuts, but it's I don't know, maybe, yeah, I can't really. Is that better? Is that worse? I don't know. Might be able to find some stuff to prop that up. There's just something. No, that's alright. It's a nice top down. My head doesn't get in the way. Yeah, we're able to repurpose the camera that used to be watching the scope. Basically just got it hung above the bench. Now it's really light, really small. So that's what made that possible. Trying to hang the regular camera over top, never. That would never happen. But I'm glad it's working for you. I'm glad you like it. Okay. These diodes are done. Controllers also done. Looking for the red LEDs. Here they are. Three of them. Getting them flipped around. Yeah, I'll switch to the other one for a sec. Yeah. Yeah. These have a little arrow on the bottom indicating which side is ground. Just gotta follow the arrow, and if you're doing that, it's not too tricky. Alright. Yeah, just like being able to flip back and forth. Keep the view fresh. There it is. Diodes installed. So I believe we need, what is that, C8, C9? Is that what's next? Just need our feed forward. Yeah. C8, C9, 0.1 mic. No problem. 10.1. There it is. So you're gonna need 6 of those. There's 4, 5, 6. 6 of the 0.1 mic, and we're going to need the 470 picofarad. C11? Yeah, is that in the same? No. Is that a different rack? .470 picofarad. This one right here. There's 3 of these. Ooh, we're running low. We need to grab a couple more. That's alright. Yeah, so you might have noticed the color code. They used to all be red, but yeah, we had a little bit of time to work on the rack, so got it kinda, as they would say, kerjiggered. So we've got white for general purpose parts, white racks for general purpose parts, red for resistors, blue for capacitors. Okay, so we got C11. And then C8 and C9. One of those is the bootstrap. The other one is input decoupling capacitor for the controller itself. Oh, come on now. There it is. And I gotta say, I'm glad that I didn't pick 0402 as our default size, man. When you're soldering tiny little parts on a board like this, these are 0603, but they still feel pretty small. Cool. Onto our point ones. C8, C9. Yeah. Ooh. There we go. It's like you don't even want to breathe for fear of blowing them right off the board. No, I'm just kidding. They're not quite that light, but if you sneezed, man, they would be gone. There's nothing you can do to protect against a sneeze. Alright, there we go. No problem. Okay, so I believe R1 and R2 are next. Those two. Those. R1, yep. Okay, so I called for 0 ohm. We can make a 0 ohm real fast. There it is. 0 ohms. Just solder bridges, that's all. And then 20K resistor. Oh, hey, Tested. Oh, I'm doing really well. Doing really well. And JD, glad you like the idea. The color code? I think that's probably about the color code. Doing very well. How about yourself? How the holidays treating you? For me, what inspired this live stream was we're finishing up the main board, and I started getting a little nervous where I was like, alright, we made that first buck converter prototype. We made the first prototype, and it worked Kind of. Well, I mean, like, it made the right voltage, but there was some weird oscillation when you started to load it because the output capacitance wasn't. Yep, so we made this proto to ease some of those concerns. Basically, lets me put on the correct amount of output capacitance and make sure that misbehavior goes away. Changed out the actual output capacitors being used, added some provisions for aluminum polymer caps. We're gonna get to play with those. Yeah, so I mean, all in all, after this stream's done, I'm hoping that I will have one less anxiety in my life, which I count as a win. Let's see. All good here. We can still say Christmas here, LOL. Yeah, Merry Christmas. Just finished putting the decoration up with the kids. Oh, that's awesome, man. Yeah, I've got some garland. Got some garland set up here. Working on the tree still. What? Me? Behind? Yeah, never. But, yeah, it's on. It'll happen. Hopefully this weekend we'll get that all taken care of. Now I gotta ask, you got any like DIY ornaments on that tree? Got anything weird on there, or is it all pretty regular stuff? Just, you know, glass ornaments, Christmas lights, all that. C10, we need 10 nano. 0.01. There it is. Anyways, glad you could make it after you set up with the kids. Or you set up Christmas, all that. Yeah. I might have to flip these around. There we go. Just getting a little better access to C10 is the idea. Rather than trying to work my way around a controller and the variable resistor and everything else. I was like, maybe not. Yes. Oh. What do we got? Why is that flagged for review? That's a perfectly normal comment. Show. Why would that be held for review? Ours wouldn't be up yet if it wasn't for the kids and nothing exotic. Woof! 8 weeks. Yeah, that's a lot of joy in one house. Oh my goodness. Yeah. Oh my goodness, yeah. If I remember correctly, when I was that age, I was running around basically trying to electrocute myself. I not knowing what I was doing. Just messing around with the outlet, giving my mom heart attacks, all that good stuff. A few ornaments. Oh, wow. Wow. Cool. Congrats, man. Congrats. Yeah, I suppose that's true. Having the family makes that a little more of a priority. Ferrite bead. Yeah, we're just about ready. We got an inductor, some input and output caps, and whew, ready to go. Okay. I suppose with that, let's grab the ferrite beads. Oh yeah, and the test points. Ferrite bead. Which one do we need? We need the 0805? Yeah. And we want the 60 ohm. Yeah. Cool. Got electrocuted a few times growing up. Yeah, I don't know. That seems pretty normal. Oh boy, all out of ferrite beads. Lame. What are we gonna need? Oh, probably 6s. Wow, we're almost out of these test points too. 1, 2, 3, 4. Oh my goodness, we're out of these test points too. Maybe what we'll do, I'm just thinking about where we can get the ground clip without like shorting out the board. I think our odds are better over on this side. Yeah, I think getting electrocuted once or twice, like, that's just a part of becoming a double E. Something, gotta learn things the hard way. Stubborn. I don't know what it is. But that's a pretty common story. Alright. Looks like we're just one test point short. I'll have to use a wire for one of those. I think our aluminum polymer caps, they're going to limit the output voltage. They can't go on like a 40 volt output or something. They're limited to, what is it, 16 volts. So we can use that for like a low voltage. I think we'll do one of these for lower voltage, one of these for higher voltage. And get it set up that way. The whole point there, of course, is so for we'll see. Let me know if this is fuzzy for anyone in the crowd, but when you've got lower output voltages, you need more capacitance to keep your ripple in check than with a higher output voltage. And a big reason why is because of the CV squared, the 1/2 CV squared energy to voltage relationship of a capacitor. So basically, the higher the voltage becomes across a cap, the more energy it takes to move the voltage around. So, you know, if we're at 3.3 volts, it doesn't take a whole lot of energy to get you up to 3.5 or 4 volts, which would be pretty insane. I got to learn somehow before the invention of the internet. Wow! Born in 79, no internet. Wow, what a time. Man, I've been lucky. I've been spoiled. I don't even know what I would do. Man, I learned, not all this, but I learned a lot from the internet about electronics before I went to university. I learned a lot just doing projects online. Doing projects and watching content that was available online. I learned a ton that way. I can't even imagine. Okay, so I've got to get enough input caps. And I think we only put 2. Oh, that's what the schematic's for. Schematic's right here. I remember looking up my favorite. Oh, Tandy? Yeah. Or looking up your favorite Tandy ohm meter years ago on 440 and forgot to put the. Oh no! Oh. Yikes. Yikes. That sounds like something that'd wake you up. That sounds like an experience that'd be hard to sleep through. Well, it says we've got more. I'm just gonna put 2 of these caps on the input, and then we're calling out 1, 2, 3, 4 on the output. So the 2 on the input, 4 on the output. Oh wait, and these are the 10 mic 50 volt. Should be these guys. Oh, those are some big caps. Okay. 2 on the input, 4 on the output. Tandy. That's like our Radio Shack, right? Isn't it actually like the same brand? Is Tandy still around? Or are they totally out of business now? I know Radio Shack is quite gone. Quite gone here in the States. Okay, so we're going to build up all 3 of these. We're going to build up 2 of them the way that we have them implemented in the on the UPS main board. And I'm just going to have a little bit of fun with the 3rd one. We're going to do only the MLCCs on the 3rd one. We're just going to see how that looks. We're going to see how that does. Because we're adding in, some aluminum polymer, some electrolytic. But I want to see what happens if we don't. There we go. Looks like I missed a couple comments here. Let me go back. Oh wait, I remember looking up my. Sorry, I got that flipped all around. Wait, JD, I thought Tandy was an Australia thing. Where the heck did you get a Tandy ohm meter? Huh. That's pretty neat. Yeah, we just had Radio Shack over here. Okay. 2 input caps. Doing 4 output caps. And I'm gonna solder these to the big plane first. I think that'll be a little easier. We'll see. Thermally, this one should be a little better. The old buck. At least the IC is coupled more tightly to the ground plane in this version of the board. Our ground plane isn't any bigger, so maybe the final temperature won't really be changed that much, but it'll be as good as it can be on a board this big. And I know thermally on the main board we're going to have a massive slug of copper on the ground plane this is tied to. There's going to be plenty of area for power dissipation. Oh yeah! Yeah, I got distracted. I wanted to talk a little bit about where the UPS project is. Tandy in the UK too? way back in time. Huh. So Tandy was in the UK, and apparently some spots in the US. Interesting. Interesting. Yeah, I'm suspecting, because I forget exactly what caps we were using in the old design, but I think we were using like 2.2 microfarad caps that were like 25, 35 volt rated. I think we only had 2 of them. I'm guessing that just the MLCCs are sufficient now, especially on the input. Wait. Mainboard. UPS mainboard. Fluker now. Nice. Fluke is... You can't go wrong with a fluke. That sounds weird, but that's the truth. Can't really go wrong with buying a fluke multimeter. Yeah, I'm not quite there. If I find a good deal on one, I'll probably get a fluke. But for right now, my oh no, that's not a solder bridge you want. VN to ground. That's a perfect. Yeah, that one will make some heat. Oh my goodness. I really cannot get on that. Super great. There we go. Solder bridge cleared. Yikes. Getting around that ferrite bead to C2 is pretty tricky. Alright, there we go. That ought to do it. But anyways, so on the UPS mainboard, or all the daughter cards, basically, I pulled in the footprints just to make sure that, like, rough order of magnitude, things were about the same size, or about the right size. Because if you guys remember, we're trying to use, like, the PCIe form factor to make this thing slot together pretty easily in a modular way. So basically, we've got the mainboard with the standard spacing for PCIe cards. And we've got our daughter cards made, and each of those are 3 PCIe slot widths wide, so it's about 50 millimeters for components, which is pretty substantial. It's enough for our big old transformers and inductors and whatnot. So we've got that plan, but I had to make sure that all the components would actually like fit on the boards. Those transformers are huge, by the way. Those transformers are like 50 millimeters by like 250 by 250. They are not small. And so I actually have to use like an extended format, an extended length PCIe card that's like 16 inches long. It's nuts. It's for like 16 inches by 6 inches for like the PFC module and the inverter card. And then even the main board, there's such a big keep out for the backplane, the high voltage backplane, that like I had to use the extended ATX, had to expand it in one direction to get all the digital stuff on there supporting it. Literally did not have enough room to route all the traces. So we're about an inch and a half wider than the standard ATX. Basically, this thing's gonna be big. It's gonna be a little big, but that's okay. I'm getting pretty excited because with the exception of the PFC module, it looks like it's all going to work. The PFC we're going to have to do something weird about, just because oh, Radio Shack, pissing that one away. Yeah, they were expensive as heck, but when you just needed that one resistor and you needed it today, yep, I did that more than once. Now you gotta like plan ahead. I know, or be like me and just order way too much of every part you need and store them for later. That works too. Just build your own little stock of them. So yeah, I'm really excited to see that come together. The PFC doesn't fit because we've got so most of these cards have like, you know, the input or output and the high voltage bus, and then a little bit of like low voltage control circuitry. That's pretty easy to fit on one of those daughter cards. But where I start to run into issues is with the PFC, because the PFC has mains on the input, it has the high voltage DC output, and it's got an intermediate voltage stage, and it's got like 5 of those transformers, and there's just not enough room. So I think what we're going to need to do long term is I think we're going to need to use like the area of a computer case where you'd normally put the AC to DC power supply, and we'll have to put an AC to DC, whether it be our design or a different design. We're going to have to put an AC to DC power supply there. And if it's an AC to DC low voltage supply, we can hook that up to a second instance of the battery module and use that to generate our AC mains. And if not that, we can generate high voltage DC and plug it straight into the bus. So basically what I'm saying is we don't have quite enough room for what I was hoping to do, which is put that all on one daughter card. But man, 50 millimeters by 6 inches by 16 sounds like a lot of room until you put 8 2-inch or 2.5 by 2.5 by 50-inch inductors on it. It starts to feel pretty small pretty fast. Oh, there's a picture on Twitter of what that looks like, by the way. If you want to see how exactly not happening that was, it's at EEforEveryone on Twitter. Check out that post. You will get a chuckle out of it. I basically pulled it in and I was like, well, that seems like enough work for one day. I think it's time to call it. Okay. Alright, inductors on one side. These are incredibly difficult to solder by hand. These go great in like a proper reflow process. But when you're trying to do like point heat application, get these things on, it just doesn't work. But yeah, I'll keep chipping away at it. And layouts are one of those things where they just take a lot of time. Yeah, you got thousands of nets, hundreds of components. You just gotta scooch them all around and find a spot for them. So might be a sec before we really get that ready to go, but believe me, I am working on it. Oh, come on now. Oh. There we go. There it is. One sec, guys. I'm sure you guys dropped a comment or two. I am super what do you guys say? Sometime you just need, is that going to use some extra coupling caps between what's in the power supply? Are you talking about this board, or are we talking about the UPS? I was rambling for quite a while. This can use some extra capacitance. We're going to need to add some for the low voltage, the one we're configuring for low voltage. The 15 volt, 20 volt output, that doesn't need nearly as much output capacitance as the low voltage. Okay, so I'm going to spin these around to solder the other side. Just make sure we're getting them well. You can notice I'm sure you notice all that extra room for bulk caps on the other side there. I'm pretty sure that's what you were talking about. It's like an option. You don't have to, but you can. Okay. That looks great. Yeah, so speaking of, yeah, let's get one of these configured. So the high voltage one is good to go. That's all it needs. The low voltage one gets some extra love. Huh. There it is. Low voltage one gets a little extra love. We're going to put down one of these, 56 microfarad aluminum polymer capacitor. It's like if you take what you know about an electrolytic, combine it with what you know about a tantalum, that'll get you pretty close to how these things work. They are... Huh. Can't seem to find my, Really? Where's my electrolytics? Weird. Alright, well, we can just try this aluminum polymer. I thought I had all the parts right here. Guess I misplaced one. But yeah, so it's just lower ESR than an electrolytic, which leads to higher ripple current carrying, which is better for example, switch mode power supplies. And they don't suffer from the DC bias effect of MLCCs, which is pretty sweet. But they still don't last quite as long. Either way, they're pretty neat parts. So you can get some in chip format. They're pretty sweet. But yeah, ours are a little more regular. Get the test point soldered down and woo! Off to the races we are. Yeah, so as you probably noticed, these are what brand capacitor name? Any of the big names are fine. Like, you know, Panasonic, AVX, Chemet. They all work. They're all good. You know, if you're buying kind of sketchy capacitors off the Chinese market, where you'll really get some issues is if you get like reused caps, and especially like electrolytic aluminum polymer, they don't last a whole long while. But like if you're buying one of the big names and you're buying it from an authorized distributor, it'll meet its specs. You know, it's like you can design it in, they'll last a certain amount of time at a certain temperature. I think like Nichicon, Chemicon, they make good caps too. I think it's more about picking the right technology rather than picking the right brand. You know, if you use the wrong topology but a great brand, it'll still wear out a lot faster than it would otherwise. I don't know about you guys, but I want to get this thing going. I want to crank these things up. Got the scope, we're ready to go. I'll clean them off later. That feels like work right now. Let's not do that. Let's have some fun. Okay, so this is our spare. No. This is our spare. We'll basically just set this one aside. This is our low voltage board. This is our high voltage board. Let's do a quick ohm check on the input and output. Just want to make sure we're not about to blow something up. Okay. Well, we'll put it on the beep mode. It's got a little more. By the way, main thing I don't like about this multimeter. What is that crap? You can touch them together without it beeping. It's terrible. Anyways, looks like we're good on the input. Looks like we're good on the output. How about this board? Good. Oh, right. And I wanted to just check my diodes. Yeah, that looks great. That looks great. Yeah, we're good. We're good. Okay. So I suppose I'll probably just want to get this hooked into our DC supply. We'll use that as a common ground point. So we got that coming over there, and then we've got the familiar twisted pair coming over from our DC lab power supply. We're going to set the current limit real low. We're going to set the voltage down to about 3 volts. Ground connected. Ooh. Oh boy. This is harder than I thought it would be to get wired in. I didn't give myself much spare wire with these. Okay. That's not sketchy at all. Don't mind that. And we're gonna need the electronic load. We'll get that ready. Let's see. Where can we? There we go. That's pretty well in view. Okay. And the output. Excellent. Electronic load is powered on. Actually, let's see what our... How does our Oh, that overhead camera though. Oh, that's so much better. I think, JD, was that you that gave us this suggestion? You're the man. Yeah, there's a little bit of glare. Yeah, I'm really excited to look at the ripple performance of this. Aren't I always? I feel like I get excited about ripple performance. Gotta get our scope probe in there. And, woo, we got a lot of ground leads to plug in. Okay, here's what I'm gonna do. Okay, the scope is hooked up. What is it, this one? No, this one. We're gonna turn off channel 2. Oh goodness, I forget. Double click on the... Yes. Right. We need another ground clip. I was like, what do we need? We need something. I just can't remember what. Yeah, we'll get this coming over to our power supply as well. It's all on a common ground. That'll help me get this going. Okay. I want to make this thing stop beeping. Wait a minute. We're giving it voltage in? Oh, wait a minute. That's probably what I smell. No? I feel... Oh, there we go. There we go. Voltage. 7 volts in, 7 volts out. And if we take our handy dandy this thing, screwdriver, one of these, hopefully one of these will adjust it eventually. Alright, that's not working. We need a flathead. There we go. So now we can get this thing set to 3.3. There we go. Potentiometers. Yeah, sorry about the beeping. That was driving me nuts. Okay. Now what we've got to do is figure out how to control this darn software. Oh, I know what it was. I was clicking on the screen capture, not on the program. I know what I'm doing, I swear. I swear. We're good. So yeah, look at that output. I want to get a scope probe on the input as well. We'll put that on channel 2. That is excellent. I mean, I know we're not loading it yet, but it looks great. Might be easier to make it look great when it's unloaded, but you know, whatevs. Alright, so channel 2 is the input. And we're going to set that to the same. Now let's do 2.5 volts per division on channel 2. Excellent. Yeah, it's just a trimmer. It's just a trimmer. Yep. So, it's right there. RV. Oh, sorry. RV1, right there. Yeah, just a little trimmer potentiometer. The only reason why is because it's really cheap. Trimmer potentiometers are really cheap. This isn't really. There's a fixed resistor right next to it on the board right here, R4, and basically it lets you depop the trimmer and hard tie this to one voltage. Yeah. But the point is if we switch back over to sorry about that, to our scope, you'll notice that thing we were seeing before, that weird ripple, that like nonsense we were seeing before, is completely gone. And what we noticed is that as the output load current increased, I'm just gonna set the input to 12 volts here. As we set the input to 12 volts and we look at the output, you notice there's a little bit of ripple. That's fine though, a little bit of ripple. And as we turn on the output, let's see if I can do the picture-in-picture for you. See if I can get that. Yeah, there you go. So you can see the voltage and current over there. As we start pulling some current, you can see the scope still looks fine. Looks just fine. Whoa. Oh, sorry. Hit the current limit on the scope. Or, sorry. Hit the current limit on the DC supply. Now we're set to about 2 amps or so. Alright, there we go. Staying pretty cool to the touch so far. No real issues here. Oh yeah, that's working a treat. And now we see, you know, there's a little more ripple on the output. That's channel 1. A little more ripple on the input, but by and large, yeah, that's fine. That's just fine. Yeah. Getting up to 4 amps or so. 4.5 is what I officially rated the thing for. Should be able to do that no problem. It's getting a little warm. It's getting a little warm, not gonna lie. Rectifier and the controller, 4.5 amps. I wouldn't want to go much higher than 4.5. I just want to feel around on the bottom. Yep, it's definitely getting spread around the ground plane. Doing well. can't run without feet? Oh, no problem. I've got some feet. Do you want me to stand it off the bench? She'll be right. Yeah, so 4.5 amps, that's about all she wrote. But, woo! Yeah, that's definitely the limit. That is quite hot. But the point is, we could actually get there without going into that weird hiccup mode. I'm going to let this cool down for a second, and I'm going to turn up the input voltage, because we're really running this thing at 24. So now we've got it set to 24 volts in. We're still doing 3.3 out, because I mean that's what we're doing in the real UPS, right? This is our use case. We're doing 24 in, 3.3 out. Rivers have banks, yet no money. Oh. It can't run because it doesn't have feet. I said I'm going to run this. Oh, I see. I've heard worse. I think that's pretty funny. Cool. I'll take it. I park in my driveway. Yeah, well, I drive in the parkway. Okay, sorry. I had to. All right. Getting this thing loaded again. Just wanted to get this thing overloaded a touch. 5.3. Woo-woo! Yeah, that's the whole point, right? There's margin in like the instantaneous. I mean, steady state, we're not going to need more than probably 2 amps out of any of these converters. But it's nice to know that we've got the headroom so that if we want to build a new module down the road, we won't need to like scrap the whole mainboard. While we got this set up here and we got the adjustable output, let's just go ahead and test 5 volts, because that'll be an experience. 4.8, 5.5. This one's one that we're more likely to hit pretty hard, because this has got like a general purpose USB output. So if you want to charge your cell phone with the UPS, you can do that. Figure that's something that more than nobody would want to do. So, where's my phone? Let's do a little bit of math here. Okay, I'm just going to turn that off. Let's do a quick efficiency calculation. I'm a big fan of efficiency. I don't know about you guys, but let's see how we're doing here. So we've got a... I'm going to want a more accurate voltage measurement than that. Yeah. Let's get one of these hooks on there. Where's my... Hey, Mom. There it is. Because, yeah, this voltage measurement is pretty garbage once you get the thing loaded. It's pretty spectacularly wrong in the heat of battle. Oh goodness. That little clip has seen better days. Oh, that's never gonna happen. Right then. Alright, I think I'm gonna power this down. The alligator clip. Oh yes. It's not a day in the EEforEveryone lab without just lots of beeping. There we go. Alright, there we go. Now that's a voltage if I ever saw one. 5.01, that's pretty darn close. Okay, So I'm gonna set this to 5 volts, 5 amps. That's 25 watts. We're gonna. Oh, let's make the math easy. Oh, let's make the circuit do the math for us. I'm gonna set the voltage input to 25 volts. So if we see 1 amp on the input and we're seeing 5 amps on the output, we'll know we're getting. Missed a few comments? What? Did I miss a few comments? I can, I'll read that. I'll read that. What current are you gonna run at? It can't run without feet. Lol, GD. Rivers have banks, yet no money. I park in my driveway. LOL. I don't know. I think I saw that. I was cracking some jokes. I can crack more jokes. What was I doing? Right. 25. Okay. So. Oh, wait a minute. Getting 5 amps. So as far as load regulation, we did drop a little bit, but only a little. I want to see at light load, like if we set this to point. No, I wonder why our load regulation is so bad. Yeah, we shouldn't be seeing excessive ground shift or anything like that. I wonder if that's just like the temperature. No? I don't know. It must just be a part of this controller. But like, dang. So I'm gonna have to bump this up a little bit so we can actually. Just guessing. Wait, I want to set it at 5 amps. Okay. So it drops about 0.2 volts. There we go. There we go. Get this set to 5 amps. So we got 1.25 amps in. Dang. That's not great. So we got 31 watts in. 80%. That's not super. Granted, it is a pretty wide voltage step down ratio. Ground beef. Wait, what? What is a cow with no legs? Ground beef? You didn't even give us a chance, JD. JD, you didn't even give us a chance. Or did you? Did you wait a couple minutes? My goodness. Just jokes. You guys crack me up. You're awesome. I think we gotta switch boards. Because the capacitor we're using on the output here can only go up to 20 volts, I think. D rating 20 volts. D rate probably 12 is about where it would start to be at risk of catastrophic failure. Yep. I think that if I had to put the performance somewhere, you know, like right now, if I had to just say, it's about like this, it's about like that. I don't know. It's acceptable for what we're doing, but I wouldn't say that it's excellent. You know, it leaves something to be desired. Like 80% efficiency. That's not great. That's not great. But at least our input and output voltage ripple is acceptable now. Oh my goodness. Oh, right. We're 25 volts on the output right now. Woo! That little LED is bright. Yeah. Yeah, I know. You're so angry with me. I know. Please. Make it stop. Is there a button to make this thing not beep anymore? I want to just desolder the buzzer. Or you just apply some voltage. I think they do it for a good reason. See, I don't want to take it off because if you install backwards, if you put reverse voltage across, it'll start beeping at you before you know, totally blow it up. Vish, can you make a tuts about battery charger? Not sure what tuts means. Tutorial about battery charger? Oh yeah, we can do that. We've got what kind of batteries are you interested in? We've got a lead acid charger in our UPS project. I don't remember how much of a deep dive we did, but if we haven't, we certainly can. Otherwise, you might be interested in lithium ion or nickel metal hydride. They're all fundamentally the same thing. They're just power supplies. But you know, some battery chemistries have some nuances. So yeah, it's a good idea. Okay. Oh. The ratcheting screwdriver. There we go. 15 volts out. Let's see if I can rescale the scope. And can you visit your home? You mean like a tour? Like you want to do a tour of the home? I suppose I could. If you guys are interested in that sort of thing. It's nothing too special. Let's do the same thing. Let's get these both set up. 5 volts per division. Okay. Let's see if our efficiency looks a little better. So we're at 15 volts out. We're gonna do 5 amp load again. Well, let's just see where that. Whoa! Come on now. Why you gotta be like that? Power supply giving out on us. Why don't they just call it like a fail supply? 14 times 5, we're gonna have 70 watts out. Yeah, it should be good. Should be good. I'm gonna say a greenhouse is glass. It's clear. I'm gonna say clear. I think I've heard that one before. 1470. Yeah. Let's see if we can get up there. Whoa, we seem to have hit some kind of protection, something or other. Yeah, that's the controller hitting that limit. That's not me. That's not me. But it seems like it's saving itself, so that's really cool. Let's see what's happening. So, looks like we're getting a lot of input ripple. That's kind of interesting. So let's do a 4 amp test, I guess. $15 volt 4 amp test. This is different. This is different than what we were seeing before. What the heck was that? Oh, thermal. We're hitting the thermal limit. We're hitting a thermal hiccup mode routine, or hiccup retry. Yikes. Need more heat sink. Well, at least it's not exploding. I guess there's worse fates. But yikes. This is why I like doing tests. Oh my goodness. So it looks like 3 amps is about our limit. Just want to let this cool down a little bit. Wow. Yes, we're getting 13.3 volts out times 3 amps. That's 40 watts. What are we getting on the input? 24.1 times 1.88. 88%. So that's much better. That's what we'd expect, right? The voltage, the step down ratio is so much. It's working in our favor right now. Yeah, what is that on the scope? By the way, not sure. Let's see, let's zoom in a little bit. Let's zoom in a little bit. Oh no, 70 milliseconds, that's not right. 1. Oh, don't be like that. One second, getting the scope set up. Okay. So what I've done is I've set up the scope to show a we should be looking at the switching waveform here. I got to trigger the scope for me. Yeah, I was just getting it triggered. So it looks like what we're seeing is just, you know, input and output voltage ripple. That is quite a lot of input voltage ripple. Oh my word. So it just wasn't zoomed in very well. Yeah. I don't know, guys. Let's try to keep her positive in chat. Yeah, so it's just input voltage ripple and output voltage ripple, but it wasn't framed very well. I had to change the time. Scale to make it look a little better. But we can see that that ripple starts to get a little much. Yikes. Okay, well, good to know. So it looks like the new design, now that we've fixed the output capacitor, we can get a pretty solid 3 amps, and that number sounds familiar. I think that's not too far off from where we were before. We might, is it imp? I don't know, our output ripple looks pretty acceptable. Let's flip our DMM. You guys see the DMM? Yeah. Gonna flip that into AC mode, try to measure the ripple a little bit. About half a volt. It's not half bad. It's not half bad. But adding a little more output capacitance will certainly help. That is not what I expected to see. I expected to have absolutely plenty of that. Thankfully, we've on the main board, we've got some distributed capacitance. We've got some extra electrolytics. So I'm not too worried about that. And it seems like thermally, we can handle about 3 amps before things start to get out of hand. Looking at the output voltage, this droop is driving me insane. And there's not really a whole lot we can do about this load regulation unless we do some pretty creative things. Like, right, we'd want to add current into the feedback to like boost the output voltage a little bit. And that is just going to be a pretty difficult thing to do. Because right now we've got this set to basically 12 volts. But if we turn it down, we're at 15! 2.5 volts of change? That's almost a volt per amp. That is almost load regulation. That is almost a volt per amp. That is terrible. 14.4 down to 12. Going from 0 to 3. I guess usually you'd do what? 10% to 90% load. So let's do like... Yeah, that's not much better. That's not much better. Ugh, what do you guys think? I'm unsatisfied. I'm unsatisfied. It's probably good enough. Given how fault tolerant this thing is, given that it's like switching between a low voltage standby and a high voltage output, that's pretty awesome. Yeah, that's pretty awesome. But yeah, we can definitely take a look at battery charger. A little more detail. Is there anything else you guys want to see on this? We could try to capture some transient response, but that would require me to actually know how to use the scope. I'm just kidding. I know how to use the scope. Just dropping this thing for a transient load condition, that is super hard. This isn't a programmable electronic load, so I can't set up like a... Right, this is why we need to make our electronic load project. This is why we need to do our EEforEveryone electronic load. Because if we made our own electronic load, we'd be good to go. Tested says half bridge, 2x20 amp, 400 volt FET, turning 500 watts. How much more can I push? Depends. It probably depends more on your transformer than your FETs. Your leakage inductance will start to get pretty nasty with ringing. So, yeah, you'll start ringing at some point. Given that it's 20 amp FETs, I would say you could probably push like 8 to 10 through there without it overheating. Oh, you're already at 8 amps? Yeah, it depends. Depends on your heatsink, probably more than anything. If you've got an infinite heatsink on it, you could probably get 20 amps out of it, but yeah. Cool. Yeah, I'd just keep pushing her for more until you see the ringing get out of hand. Is that your transformer using the random cores that you bought off eBay or AliExpress or something? You're like, wow, that is a really cheap core. If that's what you're pushing through there, that is pretty solid. That's cool. Yeah, hopefully I'll be able to say something pretty soon with our inverter. That's what I'm hoping. We've got basically the same thing. Well, that'd be the DCDC. We got a full bridge, not a half bridge, but yeah, hope ours is running as well as yours is now. Core is cool. FETs are warm. Yeah. Nice. The core The thing to remember, if you've got a thermal cam or you can embed some thermocouples in there, like T hotspot is usually what you're worried about. Like there'll be a hottest point like in your bundle of wires in your windings. There'll be, you know, that innermost winding that's just getting really hot because it's surrounded by a bunch of heat generators. That's the winding that you're worried about, because once that one breaks down, it'll catastrophically fail. So if you don't have a good gauge of your hotspot temperature of the core, which you can get, you know, with, you know, like thermal vision from a thermal camera or whatever. But yeah, no, I bet you can push a little harder. I'd probably start getting nervous around 10 amps because FETs are pretty notorious for having misleading data sheets about power and current handling. Definitely. But, you know, you can always get better FETs. Yeah. Yeah. Shoot some pictures out there on Twitter or something. Maybe upload a video on it. I'd be curious to see if it's like your last setup that you had with the gate drive transformers and all that. Gate drive transformers. Yeah, I got current sense transformers on the UPS. Yeah, I think you were picking up on it, Tested. We're kind of winding down here. This went a lot faster than I thought it would. But then again, this is the second version of the design, and it just kind of works. There's not much we can do about this thing hitting a thermal limit, right? That's a function of the RDS-on of the FET integrated into that controller, the diode, and that inductor. But I'll just change the schematic note, right? We'll just do our power budget with a 3 amp output, and I think we'll find there's still, you know, 20, 40, 60% margin on that, and if we've got enough margin on 3 amps, then no worries. If we actually need more current, we might need to make another DC to DC converter, but at least we got the ripple performance to be good. Like, I am super pumped. Look at that. That's incredible. And you start loading it, and of course you see some ripple. But like, dang. Actually, you know what? One more test before we call it. Because I want to see what happens if we try to run this at 3.3 volts. I want to see what happens if we try to run this at 3.3 volts without the extra output capacitance. I want to see how much our aluminum polymer cap was doing. So if we start cranking up the output, there we go. Wow. Yeah, that still looks pretty solid. So yeah, we've got enough MLCC now with 4 output caps that our ripple's still reasonable, even at low voltages. Wait a minute. If that's what we hit, I think that means we hit the stupid, like, low frequency ripple reduction mode thing again. What frequency is that? I am stopping the scope and I am putting a cursor on that, because we should be running at a megahertz, and if we're not, I'm adding more output caps. Oh my goodness, that's the same 133 kilohertz nonsense. Nope, we're adding more output caps. We're not ending the stream yet. Nope, I refuse. Yeah, it's hard to know, man. It's hard to know, Tested. Like, something like that, there's so many variables. To say, oh, here's the nameplate spec of a FET, what's it gonna do? Something. Something, that's for sure. Alright, so we're gonna populate some of these on the bottom. It's you know, especially for something like a big power converter. The whole electronics design is dependent on assumptions about the environment. Because there is an amount of heat sinking that will allow that to work really well. Honestly, I wonder, because I think these are doing peak current mode control. So I wonder if we're just hitting the peak current limit, and that's what's making us hiccup. I wonder, well, the input current's kind of nuts too. Let's add output capacitance first. If that doesn't fix it, we'll add some more input. Critical thing to note is that while we don't need as much capacitance as output voltage increases, we're also getting less because of the DC bias effect of MLCCs. So maybe we just dropped below that magical threshold. Our ripple became too high. We sent our controller into a low frequency operating mode and things got bad. It's possible. Either that, or we don't have enough input capacitance. This controller is real smart. It's really good at not blowing itself up. Sometimes that's annoying, but most of the time it's amazing. We can really abuse this thing, and it's pretty forgiving. Okay. Okay. So we added 4 more of those caps. Getting ground connected. Output voltage. Scope probes. I want to see this thing work and work well. What we, yes, is output. And then this will be our input. Could be either one, really. Based on what we saw, could be either input or output. Either that or the peak current, which is, I believe, set through a resistor. Nope, that's all internal to the part. Dang, if we're tripping that peak current, our only recourse could be adding a larger inductor. But other than that, we're kind of stuck. Okay, 14 volts out. That would be why our regulation was so bad, because we hit the peak current limit nonsense again. So it drives me nuts. All right. Yep. Yeah. Adding extra inductance will. Yeah, I'm glad to test it. I'm glad you love our streams. I really enjoy putting these on, and to be honest, like, this is, for me, like, we're just hanging out in the shop, but at the end of the day, we're left with one less thing to worry about, right? If we can be confident that our design's working well, and that is awesome. Alright, so seems like our scope is out of sync. Come on now. Run. Okay. Let's load it. Good so far? Don't. Yeah, so it looks like we're avoiding that current limit now. Look at that. Just needed a little more output bulk. At least we've actually got pads for it this time. But I'm still seeing a little bit of that ripple coming through. And I think that's just a limitation of our architecture. I know. You want to annoy everybody. I know. Here, we'll get this tacked on quick as I can. So we can make our electronic load stop beeping at us. There it is. Capacitor on. It's fired up. Okay. Yeah, so the extra inductance would reduce the slope of the current in our buck, so that might help not trip the peak current limit. But I think this was more voltage ripple induced than peak current induced, which is, I know, a mirror of one another, but the difference is important. Alright, so let's see if we have a little less ripple now. Beauty. So yeah, so now we're dropping much less. 14 down to 13.8. It's not bad at all. Okay, so note to self, at least 8 MLCCs. That is quite a lot of caps. At least 8 of those, and those are the 50 volt rated ones. On a 12 volt output? My goodness. And the third input cap doesn't seem to have really done much, but we'll throw that in there too. So that's set at the 15. Let's run just a touch hot. Dope. There we go. Yep, so we're running at about 3.5 amps. No problem. No problem at all. Check the input voltage, a little bit of ripple. Not too bad. Not too bad. Yeah. I'm glad I caught that. Oh, we almost had a supply slip through the cracks. We almost had let it slip through the cracks. No worries. We got it. We found it. Oh. You know, I just want to thank you guys for watching today. Oh, no you don't. Nope, you are not doing that while we say goodbye. I just appreciate you guys hanging out in the shop with us. Hope you enjoyed what we had to do today. I know I certainly did. Made a mess of the bench and decided to gather some breadboards and all that kind of good stuff. Got the electronic load again and remembered exactly why we need to build our own electronic load coming up. But yeah, you know, for those watching the archive, thanks. For those watching it live, man, I love hanging out with you guys, getting the real-time conversation, and yeah, if I can figure out how to send out a poll, or to buzz when you kid. Yeah, I know, right? And this one, I was ready to call it. I'm like, oh yeah, we got our current, got some power, looks great, we're gonna move forward. And I was like, wait a minute, that switching frequency is way too low. We've seen that before with this controller. That's what happens when you don't have enough output capacitance. Yeah, so, hey man, I tell you, we're gonna end this stream. I'm gonna walk right over to my computer and I'm going to un-DMP 8 of those caps, right? We've got the pads, like it's already in the design, so if it would have slipped through, it would have been fine. We basically just took this design, gave it a much bigger ground plane on a 4-layer board, got rid of the variable resistor, so I'm just going to un-DMP all of them. And yeah, on the 12 and the on the 12 and the 15, we need a little bit more because the DC bias effect's fighting us on these caps. And then on the lower voltage one, we know that 4 is enough, but we still need to have some additional distributed capacitance. So yeah, it's awesome. It's awesome. Just so you guys know, some of you guys weren't here when I was saying this. I want to make sure that you all hear it. You're going to notice that we're not doing the Amazon affiliate links anymore, and we'll be occasionally sharing that we've got a Patreon set up. The reason why we made that shift is because Amazon said we were a little too small yet for their affiliate program. But I mean, to you guys' credit, you guys have been doing an awesome job. Thank you to everyone who's using those links, clicking on stuff, because man, it was really picking up steam. You guys were doing a great job of supporting the channel through that, but they terminated the account. And I want to make sure you guys have a way that you guys can kind of contribute. So that's kind of what we're launching. It's not like just gonna keep adding more stuff. It was the old way that you guys were able to support the channel, and you really were. You're really doing a great job. That's no longer an option for us. So just trying some other stuff. Well, I mean, to their credit, we're still pretty small. Like, I don't have any hard feelings against them. I hope that if we grow a little bit, they'll let us back in their affiliate program and all that, because they've got some good stuff, and it's nice to share links where you can buy stuff. Like, I don't mind, right? It doesn't cost you anything. Just takes a little bit of time and puts a couple bucks in the project tab, so it's cool stuff. But yeah, I was a little disappointed when they made that decision. But yeah, we'll see. We'll give them some time. We'll just keep doing our thing, and yeah. But at any rate, the reason why I'm mentioning the Patreon is because the way that I want it to work is I don't want it to just be you guys throwing money away. I want you to really feel like you're getting something for it. So when we do little projects like this, like the buck converter module, like the temperature monitor, what we're doing is we're releasing the whole design package. So like, you get the layout, schematic, BOM, everything. So if you want to go in and tweak the board or reuse the design, you can just, grab the whole design, make a couple changes, and spin your own board. So if you're into that sort of thing, you can get access to all those designs, and it can save you a lot of time. So that's kind of the idea. Oh yeah, that's one of the worst things about Amazon. Like the small businesses, you mean the small shops? Yep, that drives me nuts. I wish there was a way that we could get the convenience of the megacorps without. Anyways, I'm gonna get on a soapbox. But yeah, it's not all good. But yeah, thanks for hanging out in the shop. Thanks, glad you enjoyed. We'll talk to you soon, and I hope you learned something. But yeah, if we don't have a chance to stream again, I know it gets a little busy around the holidays. I don't know if we're gonna have time for another, but if we don't have time for another stream, I just really appreciate your viewership, and hope we can do this again soon. So happy holidays, Merry Christmas. Yeah, talk to you soon. Thanks for watching. See ya.